Okay, we're just going to do an integration of a more complex equation than they do in the book. The method still applies. It's just that they miss out a couple of things in the first one they do in the book. So I chose to use this one as an example. So what we want to do is we want to find the area given under this curve, this parametric curve, between these two values, -2 is less than or equal to 0 is equal to 0. Now, I've actually already calculated the 2 points. If I actually put in 0, I get x of 0 is 1 minus 0 squared. So we're going from 1, and the y part is also 1. So point A. And we're looking for the area between that and the y-axis. X is -2, so when I put that in, 1 minus -2 squared is -3, and y -2 is -8 plus 1, which is -7, which is my point B. So that's the integration they're looking for, is the integration between those 2 points. Okay, you're not normally expected to draw it, you're not going to be given the graph. These points you don't even need to see in the question normally, but I'm going to show you what area they're talking about. It is the same area you would normally expect from an integration. So let's have a look through. Now what we want to do is we would like to calculate the area of a curve. And the traditional area of a curve is given by the integration of the y function with respect to x. Now we've done some little bits to do with this before. If I put in some values first, so we know what y is. Y is an integral in terms of t. Now, by substitution, if I've changed y into t, I need to change dx into t. To change dx's into t's, I need dx dt, which gives me one differential of 1 minus t squared, which is -2t. That means that I can replace dx, and this time we're not going to divide by this part, we're actually going to just leave it on the top. Now some of you might have been doing that before and doing a replacement when we did substitution. This time we're replacing just dx with this expression. We're not expecting it to cancel. So we can put that back into our equation with respect to t. To integrate it, we expand the parts. So we've got -2t to the 4 minus 2t, all with respect to x. And strictly this should be in brackets. Now, at this point we've got t's in, we know what the limits are as well. The limits come from our value of t. So we want to go from -2 to 0, -2 to 0. So now we can do the integration in terms of t. Just give myself more writing room more than anything else. And that means I need to evaluate. Take the -2 out. So we're actually integrating t to the 4 plus t. So that's going to give me an expression of 1/5 of t to the 5 plus 1/2 t squared, evaluated from -2 to 0. Put the values in, and we've got -2 times the 0 part, so we're doing them as 2 separate bits, 0 plus 0, and subtract from that -2 to the power of 5, which is 32 negative, odd powers, negative numbers always are negative, over 5. Add on a half of the t squared, so t squared is 4, so we get 4 over 2. We calculate the values and we get -2 times plus 6.4, change that round, -2. Multiply through and we get -12.8 add on 4 is minus 8.8 as an area. So the area they're talking about is this area here. As normal, it is the area between the axis and the curve, where anything in here is below the line is a negative area. And these blue areas I've calculated using something similar to the trapezium rule. So they're actually quite approximate, but if you take off 0.6 from add 0.6 to minus 8.43, you do get something close to minus 8.8. But there's a slight error in these two calculations. Okay, so that's doing an example using the integration and definite integrals. The other examples they've got in the book. Okay, so the second, I'm going to do their second example. Just quickly whiz through it. Actually,